Welcome back. Topic 4. Heat transfer process with multiple heat transfer modes. A. Define multiple heat transfer modes. First, there are 3 basic heat transfer modes: conduction, convection, and radiation. Therefore, a heat transfer process with multiple heat transfer modes is a process where more than one heat transfer mode can coexist. For example, in this system, there are conduction, convection, and radiation. Therefore, it is multiple heat transfer mode problem. Second, if we look back at the study of heat transfer, we started with Chapter 1 by introducing the definition of heat transfer, the equation of first law, and the solution steps. Then we dived into each heat transfer mode for new equations and new solution methods. The ultimate goal is for students to be able to identify the heat transfer modes and select or come up with proper equations to solve the heat transfer problem. Next, we will apply the general solution steps to deal with heat transfer problems. B. Example 13-5. Multiple heat transfer mode problem? There is air heater, which is semicircular tube with radius of R0 and length of L. The plane surface A1 has temperature T1 and emissivity of epsilon1. The circular surface A2 has temperature of T2 and emissivity of epsilon2. We need to find the heat transfer rate between these two surfaces. That's what we know and what needed to find out. Step 1. Identify all heat transfer modes. There's radiation heat flow from surface A1 to surface A2. Therefore, it is a radiation problem. Step 2. Make enclosure. Since the system is open at 2 ends, we make enclosure by adding 2 and surfaces A3. Now the system is closed. Step 3. Decide on 2D or 3D geometry of enclosure. By comparison, surface area A3 is much smaller than A1 and A2. Therefore, the contribution of radiation heat from surface A3 can be neglected. As a result, the enclosure geometry becomes two-dimensional, meaning we only care about radiation heat exchange between surface A1 and A2. Next, we count the total number of radiation surface for this enclosure, which is 2, because we have 2 surface A1 and A2, each has its own temperature. Step 4. Check enclosure surface, gray or black. Both surfaces A1 and A2 are gray because none of them has emissivity of 1. From step 1 to 4, we can draw the conclusion, it is a two-gray surface enclosure. Step 5. Based on enclosure category, we go to the radiation roadmap to select the proper equation for unknown Q12. This is radiation roadmap. We go through each enclosure category. This is our enclosure category, and this equation is selected for Q12. From this selected equation, in order to get a Q12, we need to find the view factor F12 first. Step 5.1. Calculate view factor. A. We start with surface 1 because it is plane. Then view factor F11 is 0. B. We apply summation rule for this two gray surface enclosure with F11 is 0. We get view factor F12. Step 5.2. Plug in numbers to equation 1. Sigma temperature to 4th power 1 minus epsilon 1 A1 1 over A1 F12 1 minus epsilon 2 A2 to get radiation heat value between surface A1 and A2. C. Example 13-6. Multiple heat transfer mode problem? Question mark. Example 13-6 is built upon example 13-5. For this air heater, now we have air flow in through the tube at mass flow rate m dot. At a certain location, the flow is at temperature Tm and heat transfer coefficient H. We need to find out how much heat per unit length must be supplied through the plane wall to maintain the surface at temperature T1. This is what we know and what we need to find out. Step 2. Identify all the heat transfer mode. There's radiation heat flow from surface A1 to surface A2. There's convection from surface A1 to airflow, and another convection from surface A2 to airflow. Step 3. In order to find heat supply Q prime to plane wall A1, we choose A1 as our control surface. Then label all heat transfer mode, radiation, and convection. We noticed all heat flow are leaving the surface A1. This leads to temperature T1 dropping. In order to maintain surface A1 at a temperature T1, we need supply the heat. Finally, we apply the first law. In equal out. Step 4. Select proper heat equation for each heat transfer mode in first law. A. For radiation heat transfer mode, we have found Q12 value from example 13-5. Therefore, the radiation heat rate per unit length is calculated from equation 2, which is radiation heat rate over the length to yield its value. B. For convection heat transfer mode, it is an internal flow convection. The convection heat rate per unit length is calculated from equation 3, which is the width of the plane wall time local heat transfer coefficient H time the temperature difference between solid surface and moving fluid. Plug in numbers to yield its value. C. Plug in numbers to equation 1 to get the heat supply value to maintain the surface at a temperature T1. D. Example 13-7. Multiple heat transfer mode problem. Another example. A boiler tube has diameter of a dt, temperature of a Tt, and emissivity of epsilon T. An ash deposit layer forms on the outside of the tube with conductivity K. The ash surface has a diameter of a dd, the temperature of Td, and emissivity of epsilon d. The combustion gases at a temperature T infinity and heat transfer coefficient H flow over the tube. The tube itself is placed in a large surrounding at this temperature. We need to find out the gas temperature T infinity. That's what we know and what we need to find out. Step 2. Identify all the heat transfer mode. There's radiation heat flow from a large surrounding surface to the ash surface. There's a conduction through the ash layer. There's convection between the combustion gas and the ash surface. Step 3. We choose ash boundary DD as our control surface because it is connected to the unknown T infinity through convection. Then label all heat transfer mode, radiation, convection, and conduction. Finally, apply the first law. All in equals all out. You look at equation 1, the reason we do not use heat rate is that we cannot get the convection heat value without knowing the flow temperature at the inlet and outlet of the tube. The reason we do not use heat flux for first law is that we're not interested in the external flow convection value at one point, but over the whole parameter pi d. Step 4. Select heat equation for each heat transfer mode in the first law. A. For conduction heat transfer mode, you need to consider whether it is wall or fin. If it is wall, whether it is a single wall or composite wall, and its geometry. Equation 2 is selected for our single cylindrical wall. B. For convection heat transfer mode, you need to consider whether it is internal flow convection or external flow convection, whether it is local heat transfer coefficient or averaged heat transfer coefficient, and which roadmap to use for Newton's number. Equation 3 is selected for our external flow convection over a blunt body of tube. C. For radiation heat transfer mode, you need to consider the enclosure, whether it is 2D or 3D geometry, or black body or a gray body, black or gray surface. Equation 4 is selected for our case, which is a small tube surface in a large surrounding. D. Plug equation 2, 3, 4 into equation 1 of the first law. This is convection, radiation, and conduction. E. Plug in numbers to equation 5, pi dh T infinity minus Td plus pi d emissivity sigma, temperature to the fourth power, T d minus Tt over natural log dd over dt over 2 pi k. In equation 5, only T infinity is unknown. Solve for T infinity. At this point, we covered topic 4 through 3 examples to show how to solve heat transfer problem. See you next time.